thought it'd be good to actually talk about the models for plasticity. Alright, mainly on this part. After you reach your yield stress, alright, it may go into this region. It may be something like this. It may be a straight line. So different material has a different plasticity region. Alright, which is mainly talking about this thing. Alright, for a rigid, perfectly plastic, alright, your plasticity region is over here. Alright, so for example, at first you may have growth over here, right now, and after that it's all the way goes straight, and we call this the perfectly plastic thing. Alright, and to the best extent, I will see that this model is very similar to your plasticine. Alright, or like these Play-Dohs over here. Alright, if so to speak. Alright, and if you apply a certain forces, alright, you always constantly yield it. So a certain stress, if you just zoom in a little more, alright, this particular stress, alright, when you reach your yield stress, you'll constantly strain it until it fails. Alright, you don't need to increase, because if you remember strain hardening, alright, strain hardening, the explanation is that once you reach your particular stress point over here, you'll require more stress to pull your material or deform your material. So every point of this requires higher stress and higher stress until the ultimate stress, then it fails. Alright, so therefore, as you can see, these models are in terms of how the strain hardening affects your plasticity, alright, or affects your deformations. And for a pure perfectly plastic, alright, you have similar analogy to pulling a mass over here. Alright, so when you pull this force, using this force, your mass will move. Same thing, when you apply a certain force, you increase the strain with a very straight line, so to speak. Then for elastic plasticine, elastic perfectly plastic means that this is the elastic zone. Once you reach this zone, you'll become somewhat plastic, perfectly plastic over here. So actually my fault on saying that this thing over here is this one. No, okay? This is for where that it actually didn't have any elastic region at all. Alright? But if you have an elastic and a perfectly plastic, then this means it's talking about this thing. And therefore, in analogy, alright, when you apply a force over to this spring, alright, at first you extend the spring until you cannot extend already. Alright? Then if you were to apply further forces, this will actually move your mass. Alright, and therefore the mass will move. So if you apply a force that is just right there, just pull a little spring and then it returns back, and then it's talking about the elastic portion over here. Hopefully you get what I mean. Because for example, if you apply 1 Newton over here, alright, you may extend this thing, but you didn't actually move this mass. So when you release, you may actually go back to this state right here. Alright, now I apply 3 Newton. Alright, when I apply 3 Newton, this thing stretch more. Alright, this spring stretch more. Alright, but this thing still haven't moved yet. Alright, so we are still talking about within this elastic region. As you can see, the more stresses you put, it can still tahan and return back to its own original state. Alright, but however, if you put 10 Newton now, you're gonna elongate already, and then instead of just this mass just this mass is not moving, you'll start to pull this mass already. So this mass is starting to move all the way. Alright, and therefore talks about the plastic region, because your strain is gonna increase and increase and increase already. Alright, so this is the example for just a model, because normally you can set up the equation, and then these are the equations that links with your so-called modeling of a spring system, things like that, and you can set up equations and then to simulate a model for your graph. Alright, then therefore I think this is the pure reason behind what we have been using for our stress strain function over here, and also maybe also related to your the Osgood law, if you remember, this one over here. Okay, your Rambin-Osgood law. Likewise, for if you're talking about just rigid linear work hardening, you're talking about this one, you're talking about another linear wood hardening, then it's something like this. Alright, where it's just the meaning of it. Rigid, perfectly plastic means that you're always plastic. Alright, rigid linear wood hardening is meaning you're always linear. Alright, elastic, perfectly plastic means that you have, if at first elastic, then you plastic. Same as this thing. At first you elastic, then you linear wood hardening. At first you elastic, and then you linear wood hardening. So this is just the basic concepts of things. And then how you're gonna deal with your stuff in the future, I don't know. Just for you to just take note of. To inform you that there's a little stuff that I actually didn't go through. For example, in your chapter 29, alright, you have to go all the way down into U functions. Alright, this U function states that your certain stress state, alright, with a certain function within your certain stress state is equals to 0. Alright, this means that the yielding starts to occur. Alright, so we start by defining the U function. Alright, this U function y in terms of a certain stress will occur when it is equals to 0. Alright, meaning at this particular point. I would believe, I don't know. So at this point, instead of just the sy, talk about that is equals to 0 or at the origin. And when you start to use things goes in a different way. I think this is the manner. And you just continue to read. Alright, is that we can assume that the sigma, our function, is equals to a certain stress. Alright, if you have a uniaxial case, meaning you are pulling in just one direction. Alright, so one active stress, and therefore you have to bring and as for uniaxial loading, then you're gonna require the minus of the instead of just the pure stress component, you're gonna minus away your U strength. Alright, so your stress minus your U strength will be equals to your this function, where this function, if you still remember, is equals to 0. Alright, is equals to 0. Alright, and therefore from here you can simply say that the sy is equals to your sigma. That is what we have always said. Alright, and instead of writing that, alright, I divide everything by sigma, the sy. Alright, so sigma minus sy is equals to some function. I divide everything by sy. So what I have is sigma sy minus 1 is equals to y over sy, where y we know that it's 0, so everything still goes to 0. Alright, so therefore this thing over here is this thing over here. Just that this is sy. Okay? You know that this thing over here is equals to 0. Alright, this thing over here can be also equals to 0. Alright, as long as your because you know that sigma is equals to sy. As long as your sigma is equals to sy, this means that sigma over sy is equals to 1. Alright, because if 2 over 2, then it's equals to 1, right? So even if you square it, 2 over 2 square is just 1 square. Alright, so that's why we can write, instead of sigma over sy, we can also write it as sigma over sy square minus 1. Alright, so this thing over here, as you can see, somewhat correlate. Alright, this sigma later on will become sigma m over your U strength of a material. Alright, if you were to take a look back, similar to your Rambert's or Scoot law, where you're talking also about the von Mises stress over your U strength. Alright, you have to compare. Alright, so as you can see, it's the same thing. Alright, and this understanding somewhat talks about the distortion thing, or the distortion energy theory. Alright, but I'll not go into there because as you can see, this is also being reappeared again. Alright, so it can be used, so that particular distortion energy theory, alright, this particular one over here can be used. I don't know whether is this a distortion theory or what, but it's just some functions telling you that you can represent any of a stress state using this equation also. So therefore we use it in the von Mises and things like that. And there are little things that I didn't actually read it out, so I highly suggest that you read it out if you're free, and provided that you understand, especially the equivalent, all these things. I don't even know how this thing works still. Alright, but therefore these are all the things that I really need to know. I shall see you soon.